Thank you. Being placed into conference in muted mode.
Participant to this webinar about fact services. This delivers micro-nano-fabrication and characterization services for research and development. And today's webinar titled Semiconductors and Polymers and Metals. Oh my! Thin Materials Processing Services. The second of 4 webinars in this year's series, where each webinar focuses on one set of capabilities for nanofabrication. Andrew Fung. I'm a Client Technology Advisor for Microsystems and Nanotechnology at CMC Microsystems. So I will open this webinar by introducing Canada's National Design Network and CMC's Microsystems, and tell you briefly about fact services, how the program works, and you can start a project. We have a very interesting lineup today, and you'll hear from engineers at 4 labs within that network. Ed Wu from Toronto Nanofabrication Center will begin with a presentation of thin film processing techniques that are offered through fact services. And each one of the labs in the network will showcase examples of R&D projects that are enabled by specific in-house capability. So, silicon vias presented by Aaron Hrishu at Nanofab, University of Alberta. Then surface micromachining by Alireza Mezgar at GCM, or Thin Films Group at Polytechnique, Montreal. Photonics components presented by Marie-Jo Ligour at 3 Lab at University of Sherbrooke. And finally, Edward Xu at Toronto Nanofabrication Center will present process for high-pressure, high-temperature microfluidic chips. Find as you go to this webinar that you can access the capabilities at these labs for custom fabrication projects. Feedback is welcome throughout the presentation. If you have questions or comments for any one of the panelists, please use the chat box in your WebEx interface to send comments. So with a brief introduction to Canada's National Design Network, Microsystems is headquartered in Kingston, Ontario, with some additional offices in Ottawa and Winnipeg. It consists mainly of 2 elements, infrastructure and a path to commercialization. And these 2 form the core of CMC's mission, with a 10-year outlook to a thriving advanced manufacturing landscape in Canada. Now, with this framework, CMC acts as an honest broker of technology and know-how. CMC manages Canada's National Design Network, which is essentially a community of faculty members, micro-technology facilities, industry partners, suppliers, both within Canada and around the globe, and a community of postgraduate and undergraduate students. There's technology access for typing. Last year, we saw 200 CAD tools and 400 prototypes resulting from design activities at global companies and Canadian university and government labs. In addition to the prototyping technologies, CMC also offers a loan pool of test equipment, training events throughout the year, R&D projects, and infrastructure installed at universities across the country. Clients can access CMC's offerings via subscription. In addition to that, industry clients can access these technologies also. So last year, around 25 projects were delivered to industry clients. CMC's portfolio for prototyping, Fact Services delivers R&D solutions from qualified university nanofab labs. Now, services exist to put technology for research and innovation in your setting. That's a university lab yourself or in the R&D setting. At the URL at the bottom of the screen, you can access a recording of previous webinars with DOOSPAC services, the labs involved in the work, Now, you see yourself in this scenario. Is a company looking for early stage production, and on the right is a university researcher with a new invention, seeking more and reproducible processes to improve the prototype. So both of these parties want a proof of concept, to design and then design to prototype. They may need expertise, bandwidth, a special lab with equipment for a particular exploratory process, or perhaps a larger company needs a low-volume, high-mix laboratory environment to test out a new process or material. Well, this connects the technology developer in a number of settings with a network of labs that are equipped to meet kinds of needs. So this is the fact service landscape, how you can take your idea from a sketch to a successful prototype. A typical flow of fact projects moves from left to right in this view. Start with academic or industry client requesting services, each with CMC and a lab to build a dedicated project in consultation with members of the FACT network. And the project is implemented in one or more of the labs with a common service protocol for quality and design environment. Now, the network is in formative stages today and is open to growth, so other labs join the network in the near future. And for commercial-facing technology, projects can benefit early on from alignment and compatibility with downstream partners for production. Services will collaborative and responsive consultation of service from the labs for those projects that so desire a possibility of alignment with low-volume production downstream. And this can include a number of things: design consultation, development of a process flow, cut fabrication, and of course even low-volume production. This in the labs bring not just the technical capability, but their expertise in a number of microtechnologies. So on FACT Services website, you can download the full catalog of service capabilities. Included with FACT Services is easy from the Start a Project page. Every project will progress with the involvement of the client and the entire delivery team. So the client starts by sending a request form with details of the services requested, including things like critical specifications, a drawing, a layout, the number and type of samples required. That concludes the introductory segment. Now I will hand the presentation over to Edward at the TNFC.
Hello, you can hear me? Okay, good. Hi, good afternoon, everybody, and thanks, Andrew, for the introduction. And today, my talk will cover the material processing technologies and the services through the FACT program. And I talk about the state of the art, the microfabrication technology. Here I show you the two typical examples. One is the 0.13 dual wire CMOS technology. You see multiple layers on top of the silicon. These include many layers of alignment and hundreds of steps of microfabrication to build up this structure. And this digital micromirror device is a MEMS structure, which involves also very many complicated processing technologies. Only the IC fabrication at the bottom, but also on top of the IC layers, you have all the mechanical structures built up. So to make these structures, you will probably go through all these steps listed here. So today, I think last time we talked about patterning through the Factor Labs, with a whole suite of the lithography methods. And today we just focus on the two important steps. One is the subtractive process. It involves all kinds of etching, wet etching or dry etching. Also additive processes involves physical or chemical deposition processes to add the materials on top of each other. And in addition, we're going to cover a little bit about diffusion implantation or surface treatment to modify the material's surface properties. And first step, to start your fabrication, you will use the wafer cleaning steps. There are typically two of cleaning. One is for the silicon, so RDA three-step cleaning is the most important step. Start with any process during the fabrication. Before the high temperature process, you must go through the RCA three-step cleaning. And second cleaning, that's after the bulk process on silicon. Usually it involves a low temperature processes. That you just use the solvent-based cleaning steps. So in terms of, I'm just talk about maybe three typical subtractive processes for make the pattern to the materials by etching. The first bulk micromachining. Bulk micro involves the etching, remove the silicon materials. So because the etching rate is strongly dependent on the single crystal plane. So the anisotropic etching of silicon can be done using the KOH and the EDP or TMAH, which is a CMOS compatible etchant here. And typical applications, you can build up many kinds of geometric structures on the silicon. Here it gives you a typical example using the bulk micromachining, make the micro printing head. And here IBM also has a technology to use gas-phased isotropic silicon etching to remove the material underneath the copper metal to make MEMS switch. Just to give you an idea, I think there's a lab in Alberta Nanofab. They have this gas-phased. The other labs that also has that. Still doesn't have this yet. And surface micromachining, typical steps will go through from the depositing a sacrificial layer and a pattern on the sacrificial layer and the deposit structure layer, and then finally remove the sacrificial layer to release the structure. So it depends on the application. You will need to select which material will be used for structure material, polysilicon. These give you a typical example of this table. And the third subtractive process is deep reactive ion etch, DIE, to allow you to dig deep into the silicon material and with a very high aspect ratio, and it has no constraint in terms of how deep you go. And it's for the MEMS applications, the feature size, usually it's relatively big. But also in our new DIE system, it's the Oxford Instruments, the Astralis 100. They allow you also not only do the Bosch process, we also can do the cryogenic silicon etching. Instead of etch the material at a regular temperature range near 0 degrees Celsius, we can cool the substrate down to less than minus 100 degrees Celsius to allow you have a really smooth sidewall, and so you still can do deeper silicon etching, and also you can control the profile of this sidewall by this kind of compound as a polymer. This polymer is interesting. Once the temperature of the substrate rises to a certain temperature, they evaporate, so there's nothing built up at the sidewall. So now let's move on to add materials on top of each other. So the additive processes involves physical or chemical processes. So physical process, you have the evaporation or sputtering basically, and the chemical process, you have the thermal oxidation, grow oxide, and the CD process, and finally you also have a spin coating process, a kind of a soft chemistry process to build up nano materials. First of all, let's talk about E-beam evaporation. I think through the FACT labs, for example, through the IT Nano, you have a whole bunch of material you can select to do the E-beam evaporation. And at TSVS, we have a similar ones, but we're in a new combined thermal and the E-beam evaporator that supposed to do all these materials up to 6 inch, and the substrate temperature can go from room temperature to 400 degrees Celsius. So the tool will be ready by the end of this year, I think. And sputtering, we have a new sputtering system through the Age International, go up to 6 inch and the substrate temperature go up to 850 degrees Celsius, and they can do reactive sputtering or co-sputtering. So these are the materials we have right now, excluding YBCO, but this system can allow us to do the YBCO superconductors to deposition at the high temperatures. And the 3IT, for example, they can do all kinds of these materials as well. Okay, liftoff process is also an important process combined with the lithography with the deposition. Especially for those materials that's hard to find the proper etchant for the etching. So you use a liftoff by put the resistor pattern and then deposit the layer of the metal, and finally use solvent to remove the resist. And there are two types of resist. You can usually use negative resist to form a retrograde profile, but you only have the positive resist, like this resist. You can first expose it and then further exposure to overly expose it to firstly create this retrograde the profile for the lift-off process. And it gives you an example that that's done by the CMC CFP. What is it? P? I forgot. So this is a technology available through CMC gallium nitride process, and now move down to maybe 500 0.5 micron. The final layer of the gold metal metal was done by liftoff. This is a device we developed through this technology. So see, we built up the air bridge of the gold nicely to avoid the field clouding to improve this device. It's a aluminum nitride HAMT device to read the breakdown voltage over 500 volts. And in addition to use liftoff for the metal patterning, we also can do the electroplating by polarize the pattern and on top of seed layer. Then electroplating and then remove the resist. Here's your example at the 4-inch glass wafer. We can pattern the gold, electroplating gold with a 3 micron gap and a 20 micron thickness of the gold. Different materials including nickel and copper can be also plated. And oxidation, we have the furnace here can do the batch processing of the oxidation of 4-inch wafers. We can do the low-cost process, the semi or full recessed low-cost process is still a very important process for the either for the optical or the circuit applications. But after the 0.3 microns, usually you are not going to use the low-cost process. Instead, you will use the STI or DTI isolation techniques to isolate the transistors from one to another to avoid the latch-up process event happen. So it gives you the quick sketch about the STI and DTI. Basically, you need to use the trenching into silicon and then oxidize and refill with the silicon oxide and the polish. Use the CMP chemical mechanical process. DTI, instead of filling the trench with the insulator, you fill in the polysilicon. This be deep as like 7 to 8 micron deep. These STI may be 0.3 micron deep. It gives you the state-of-art, the silicon germanium HBT through IBM. You see the DTI and the STI here. It's silicon germanium HBT just here. All right, you can see from this comparison. This is with CMP process, and this is with CMP. CMP process allow you to build over 10 layers of the interconnection on top of the silicon, and still you have a high resolution in terms of lithography. All right, and other special technique, including the epitaxy, to allow you to grow very perfect line thin film on top of the substrate. For different purposes, nowadays people are growing galvanized nitron silicon for many applications, for high speed, for optical applications, and of course the SOI also need the epitaxy. So they basically technology MBE, MOCVD, or high vacuum CVD for silicon germanium epitaxy. I think in university, I think Professor Luda's office, the lab, has 2 kinds of epitaxy course. And Professor Luda is going to be our director, and I think from July this year. On the ion plantation, it's a quite expensive setup. I think through Factor Labs, we have 3IT and GCM has this equipment. If you need this type of service, you can contact the person. They are going to give a presentation afterwards here. And here are some examples by combining the typical process to enable some technologies. For example, to produce SOI wafers, you can use oxidation, ion plantation, epitaxy on the CMP for example, here use CMOX, the implantation of oxygen into silicon, and here you will form a buried oxide layer to form the SOI. And if this layer is too thin, you can actually grow by epitaxy. This one, the smart cut process, by instead of implant oxygen, you implant in hydrogen, and form the hydrogen bubble layer, and then separate them and bond into and separate the SOI. This is also very popular technology. The very conventional one is BSOI. This process involves oxidized wafer and bond the oxidized wafer with the silicon wafer, and then either growing, etching, or polishing the top layer to a certain thickness according to the requirement. So this BSOI process allows all kinds of SOI materials for people's, especially for MEMS applications. Another example, for example, with SOI materials, DRE, oxide etching, you can, for example, from the MEMS devices using this SOI MEMS processes. And want to have details. And for example, this one is called a SCREAM, single crystal reactor etching and metallization. Involves all these steps. So you have the oxidation, the pattern, and the etching, and finally you at bottom and use isotropic etching of the silicon. Finally release the structure. People use this technique to make many accelerometers, many kinds of MEMS devices. Okay, and to modify surface property of materials, here just give you an example. The surface treatment and PDMS bonding. This is for microfluidics. Right now, it's very popular. So, can plasma treatment of the PDMS or the to make the surface of the material become hydrophobic. This one, like Teflon, it's water on top of it to become a ball. And the hydrophilic become very flat. So here's the typical process steps that we can do here. Mold the PDMS and then bond it to the glass for them in microfluidics. Okay, so we covered the etching and the film depositions. So many details I cannot cover because of time. So just quickly list the process we can do through all the labs. Over the NanoFab, they have a whole bunch of the deposition tools and the etching tools. I love etching tools here. You can go to their website and find the capabilities you're looking for. And GCM labs at Polytechnic Montreal, they have also a whole bunch. They're quite similar, but the lab has some unique capabilities. This is a 3IT Nano, gives you a whole bunch of the deposition processes and access. And this is finally that at TMC. You can go to our website. If you need any consultation, just contact me. So if you have any questions, just raise through the web. All right, that's all my talk. Yeah.
Thanks much, Edward.
Okay.
We're going to pass the presentation now on to Aaron Hrishu at NanoFab, who will present a example of through silicon vias using RIE and LPCVD techniques.
All right. Thank you, Anne, for the everyone can see my screen here, I believe. So one of our application examples involving thin film processing is indeed through silicon vias, but I'd also like to discuss two upcoming capabilities that will be coming online in the next few months. As with all of the other FACT labs, our toolset does provide most of the standard thin film processing capabilities for dielectric, metal, and organic deposition and etching from oxidation, CVD, PVD, plasma, dry, gas phase, and wet etching. As Edward mentioned, you please refer to our website for a more complete listing of our capabilities. One thing I'd like to point out for its relevance to TSVs is that of boron-doped, in-situ doped CVD poly silicon. So why are people interested in through-silicon vias? Well, as the name implies, these are electrical connections that extend all the way through a silicon wafer or a handle wafer, for example. These open up the possibility of vertical integration in addition to the usual planar integration for integrated circuits. So this allows you to have stacked ICs to have 3D IC packages. So why this may be interesting, there's a host of benefits to this. The shorter connections affords you improved packing density and noise immunity, greater or reduced power consumption, faster overall device speed. And when you think about it, there's really no reason why each of the individual chips needs to be the same type. So you can have heterogeneous stacking to pack more functionality into a single package with a smaller footprint. So, for example, you could have logic in one chip, memory in another chip, and RF for instance, photonic capability in a third chip. This is just an example of an SEM from literature of such a structure. Now, while TSVs have started to take off within the last about 8 or so, it's interesting to note that the original patent was filed in 1962 by William Shockley. He's the co-inventor of the So for TSV fabrication at the NanoFab, this was a project which was done in collaboration with the Acadian Group at the U of A and an industrial client. This is just an example process flow using a SOI substrate. Depending on the type of device you want to fabricate at the end of the day, this may vary slightly. But essentially, you start with your SOI. You use a deep silicon reactive iron etching Bosch process to etch your vias through, stopping on the bare oxide, do oxidation to provide insulation, through to provide contact to the oxide. And then the critical step, we backfill these vias with a boron-doped polysilicon. Now, the wafer is planarized with a mechanical polishing, and now you have your contact between the back of the wafer, each vias, and the silicon device layer, which can then be patterned to make whatever sort of device you're interested in, MEMS or what have you. Now, I'd just like to point out that CMP, we do not currently have that capability in-house at the NanoFab, but it is available at other FACT labs. So for this process, this is a ICP or IE tool which is used for some of the deep silicon etching in this project. Then SEM images of various parts. This is an example of the via, and you can see the scallops characteristic of a Bosch etch process. And you can see the handle wafer, the silicon, which has been oxidized to provide insulation, and an incomplete polysilicon fill. So eventually, at the end of this process, this via gets completely filled with the polysilicon. So, as I said, while we used this tool for some of the etching tests in this project, we're excited to announce that we were installing 3 new plasma etchers in the near future, which will help to do this type of process or other deep silicon etch processes at NanoFab. This image, it's not a live video feed, but it might as well be, as we've got some of our process specialists who are currently doing qualification on our plasma Australis from Oxford. This is a recent example, so we were able to go through about 4/5 of the way through a wafer in about 40 minutes. You can even go through if you have larger features. Now, in addition to this sort of high-rate Bosch etch, we are also qualifying a very smooth sidewall etch where the scallop depth is only about less than 30 nanometers. So in addition to the Australis and our RIE tool for oxide nitride etch and ashing surface activation, we're also in the next few months getting a Cobra. This is a chlorine etcher from Oxford. This will enable metal etches, 3-5 materials, and diamond, other more exotic materials for etching. So check back with us in a few months, and we'll have some updates on our website about these new capabilities. Now, one unique capability, which is also coming online within a few months, is that of glancing angle deposition. These are GLAD films. Now, this is some a couple of systems which were recently acquired, inherited from the group of Brett at the University of Alberta, who's recently retired. So imagine a standard electron evaporator, but instead of placing your sub horizontally, you place a really oblique glance angle to the vapor flux. You get a self-shadowed growth mechanism for the film. Now, what that enables you to do is, by just choice of both this angle, substrate angle alpha, and also the substrate rotation phi, you're able to tune the nanostructures of the film. So you can go from angled oriented pairs to square helices to round helices to vertical columns. And you can also change the overall porosity of the film by varying alpha during either keeping it fixed or varying it during the deposition. So we're very excited to be able to offer this within the next few months. We're just installing the tools, and we'll start qualifying those soon. So yeah, check back on our website, or send me an email if you want to get any more information about that. I'd like to just acknowledge the NanoFab staff director, some funding agencies, and for any service requests, either Fabrication, contact myself, Aaron Rishu, or my colleague Hang Lee for any characterization services. All right, thank you.
Thanks much, Aaron, for that presentation. Next, we're going to go to Ali Reza Mezgar at GCM, the Thin Films Group, present about R&D examples in surface micromachining. Now, set up, I just want to take this opportunity to remind the participants in the web today to see questions you have about the content you've heard through the window.
Okay, do you have the voice and the presentation?
Yeah, I can hear and see you fine. Go ahead.
Okay, there we go. Hello, my name is Ali Reza Mezgar. I am a research associate with the Microfabrication Laboratory of Thin Films Group, GCM, in Montreal Polytechnic. Today we'll give you an overview of surface micromachining technique. Ed has already introduced surface micromachining in his presentation. As he mentioned, it is a powerful technique to fabricate fixed or moving suspended structures such as beams, cantilevers, bridges, mains, and conduits. Surface micromachining in its simplest form needs two layers: a sacrificial layer at the bottom that will be eventually removed, and a structural layer that the structures to be suspended are patterned in it. Depending on the device and application, a variety of combinations of sacrificial and structural layers are possible. Common sacrificial layers include silicon dioxide, various metals, polymers such as resist, PMA, and polyamide. While polymers are also used, but they are less common. Structural layers are silicon in monocrystalline and polycrystalline forms, silicon nitride, metals, and permanent resists. The removal of sacrificial layer that is called the structural release can be done by wet or dry etching. Several important points to consider when designing a surface micromachining process. You have to make sure that the sacrificial layer is compatible with the deposition technique to be used for the structural layer. The release technique should be very selective to the sacrificial layer so that the structural layer is not damaged. Very important to provide release holes for large structures to facilitate the release. Otherwise, many difficulties might arise. In the design and simulation phase, we need to consider the effect of the residual stress of the structural layer to prevent undesirable surprises after release. Might encounter some challenges in surface micromachining release steps. Very large structures or structures with very small release holes are difficult to release, and it will take a long time to release them. problem is a stiction that happens due to the surface tension of liquids, normally water, used to rinse the device after being released. Resulting collapse of the structure that was supposed to be freestanding. There are many solutions to these challenges. The use of a surfactant can facilitate the release of a structure with small dissolves. Alternative solvents with lower surface tension can be used to prevent the stiction. Dry is another way to avoid stiction. Another common technique is critical point drying that takes advantage of the fact that in the supercritical state there is no surface tension. Other solutions that are less common but are still useful, such as freeze drying, layer phase etching, surface modification, making the structure stiffer, and finally using anti-stiction structures. There is a very common surface micromachining configuration in MEMS that's using silicon on insulator wafers. As Edward already mentioned, SOI wafer normally consists of a single crystal structural layer and a silicon dioxide sacrificial layer that is released in a hydrofluoric acid solution. I'll give you two examples of surface micromachining using vapor phase HF release. CM. The equipment used is quite simple and consists of three parts: the reservoir, the reaction chamber, and a heating chuck. The sample can be held on the heating chuck by mechanical or electrostatic clamping. The chuck is placed upside down on top of the reaction chamber that is partially filled with HF solution. Example 1 shows a thin silicon cantilever on a SOI chip that's released by vapor HF at 40 degrees centigrade. The sample shows a silicon nitride photonic crystal membrane with a sacrificial silicon oxide layer, processed by vapor HF etching at 60 degrees centigrade on top of a support wafer. The structure has initially been designed for wet etching and critical point drying. As there are some problems encountered in wet etching and critical point drying, vapor phase etching has been tried. Solid residue has been observed after the release. Further studies showed that the residue is the product of reaction of silicon nitride with hydrofluoric acid that is water soluble, so easily removed in wet etching. To remove this residue, the sample went through a long vacuum annealing. The results after vapor etching and after annealing are shown here. Here is a summary of GCM thin film deposition capabilities that cover the deposition of metals, dielectrics, and organic material. The upcoming capability, that is the LPCVD furnace, that will be installed gradually in the coming months. And the thin film etching capabilities at GCM covers pretty much everything in wet etching and dry etching, and all chemical mechanical polishing. Facilities are open to all academic and industrial clients. For further details, I invite you to visit our website or contact me or my colleagues. Thank you for your attention.
Thank you, Ali Reza, for that presentation. Next, we're going to Marie-José Gour at 3 NAB, University of Sherbrooke, and she'll be presenting about processes there used for photonics components.
Hi everyone, can you hear me well? Okay, great. So what can we do at 3IT Nano? So as you probably saw from Edward's presentation, we have a broad spectrum of material that we can deposit with various machines. We can also dry etch most of these materials, not all of them of course, with either IC etching, barrel IRE, or ion milling. And we also have various miscellaneous processes where we can do wet etching, specific ozone cleaning, for example, or liftoff, to pattern all these materials. Now, we have all these nice building blocks, so how can we assemble those to actually make a device? So here's an example of a nano waveguide that we've made off of gallium arsenide, aluminum gallium arsenide devices. So we have a standard recipe for gas etching, but for nano waveguides, we need to make sure that the verticality is almost perfect and that the side robustness is really low. So we've modified our existing recipe to etch these nano features. Now, in doing that, we can actually make some second harmonic generators or 2-to-4-wave mixing devices. So we dry etch the mask, we dry etch the waveguide, and there you go. It's not very complicated, but you do need to adapt your building blocks to whatever device you want to make. Another example is nitride PCVD nitride. So we've made some thin planar silicon nitride on oxidized silicon. So we've actually fine-tuned the recipe in order to change the index of refraction and the absorption coefficient of our nitride. And doing that, we managed to have some area where our propagation losses were less than 1 dB per centimeter, which is actually a transparent material. So based off of this research, you can actually design a more complex system, such as an anti-reflection coating for a multi-junction solar cell. So multi-junction solar cells are multi-junction because each junction actually converts the solar radiation of a specific wavelength range. And all of these junctions have the same conversion efficiency. Now, when you're actually putting on an anti-reflection coating, you may want the reflectance to be wavelength dependent. So having the flexibility to tune the index of refraction and the absorption coefficient of a layer, that you can actually control the thickness, and then you can control multi-layers of such a material that would actually allow you to fine-tune your reflectance based on the actual device, so you can actually come up with a more complex system, complex anti-reflection coating that actually doesn't just reflect or absorb a specific wavelength, but a range of wavelengths. So these are just typical examples of what we can do if you take a basic building block, an etching recipe or a deposition recipe, and you adapt it to whatever device you want to do. In doing that, you can actually gain a lot of flexibility in terms of what you can do, either being a photon cage, a based LED, or an ENP-based ring laser. So if you have any questions, don't hesitate. You can actually see where you can actually access our website or my email address. Or you can actually send also any questions you may have to Andrew at CMC, and he will relay that to me or whatever fact lab that's really responsible. Thanks everyone for attention.
Jose. Now we're to go back to the Toronto Nanofabrication Center, and Edward, he'll present a process for high pressure and high temperature microfluidic chips.
I'm coming back.
All right, go ahead, Edward.
Yes, okay. So this is the last topic. It's high pressure, high temperature microfluidics. I just recently developed this process module. I just want to go through the details of the process. Process flow is like this. So starting with the silicon wafer, usually it's a 1 millimeter thick silicon, single side polished silicon wafer, and you use a photoresist. We use a Shipley resist S1818, 3000 RPM to have a of the resist about 2 or 3 micron thickness, and then you pattern it, and then you use this resist as a etch mask and your DIE, because the high selectivity of the recipe and the tool. So that 2 micron thick resist allow us to dig really deep through even the 1 millimeter silver. depends on the application. We can control the depth of the channels they like. So in most of the applications, they just need to dig down to 200 micron channels. And after the etching, just simply remove resist and then use a prana cleaning the wafer, and then anodic bonding with a borosilicate glass, and the bonding, and you just use a hole, drilling the holes to feed the microchannels and the dicing, and then assemble for the test. So just to give you a couple of examples of the chips developed by this technology by Professor Sinton's group, they for this type, it's used for mimic what happens underneath the surface of the Earth to simulate a temperature maybe around 400 degrees Celsius, and the pressure will be over 1,000 psi. So this one is for carbon dioxide oil miscibility measurement chip. The holes they feed it through their system for testing under the microscope, so they can see what happens through the channels or by actions. And or maybe too big. Do you see this picture? The screen is too big. Maybe. So this is an example. They use the same technology and to simulate the sandstone pore network chips. So there's a network of those channels, and then there's a test set up to simulate what happens under the ground through these structures. This one is for another project of this same group. So by oil extraction chip. So if you see here, the 1 millimeter thick silicon has been added through, so you remove the center part of the chip to isolate the thermal conduction along those sensitive channels. It can still is even, so it can really etch through the silicon wafer by our technology. And another project, final example, is by the water user, Universal Water Professor Caroline Ren's group. They actually observed the liquid carbon dioxide and water in this channel at a high pressure as well, and the temperature may be it's 50 degrees Celsius. Yeah. So just to give you these examples, and you can think about your application and contact us. And if you need to develop any microfluidic devices using this technology, we're happy to provide service. All right. Let me hand back to Okay.
Word. Okay. So just in transitioning the presentation, again, there was one question for Aaron regarding the glancing angle deposition technique. Could you speak to some of the applications, maybe the most common applications you've seen for the glance technique?
Sure. Well, I will preface this with a qualification that I haven't used them myself yet. It's still being transferred between labs. But one application which is easy to understand is that by changing the rotation, either by changing the rotation direction during the deposition, you could, for instance, make strings with a certain type of handedness. So, for instance, a left-handed helix or a right-handed helix. Now, if you make that out of, for instance, transparent material such as glass, or you could, you essentially make an optical filter which has it has chiral polarization response. So, there are applications there for custom filters with particular optical responses for left and right circularly polarized light. Probably more common is using the springs as springs, so making silicon or copper or some other metal nano springs, which could be used for whatever mechanical purposes. You might cushioning effect or something like that. So those are two such examples. What else? By has columnar structure, you can introduce a lot of surface area, which could be useful for optical absorption or for supercapacitors, for instance. So those are such examples. I would forward the read to take a look at the Michael Brett Group website, which is still up. They've got a bunch of examples there which may be of interest. I forward some more references if they'd like to contact me personally.
Great, thanks, Aaron.
Yeah.
I want to invite the participants in this webinar to stay connected with CMC Microsystems about news for the next two webinars in this series. They're coming up in July and November, one about metrology and materials characterization, and then the 2nd November about packaging and assembly. And again, each one of these webinars will present Fabrication's capabilities available for researchers to access. There may be a question about the cost of the services you've seen today, how they cost, and are discounts available to researchers. So all requests for services are priced based on quotation, given the custom processing that's required. And programming subscribers can benefit from discounts through a peer review system. The discount is determined, the amount of the discount is determined case by case. We've seen prototypes where the cost to the client will range from $1,000 up to, for some large projects, over $10,000. Okay. So that, I'll just close with pointing you to information about Fabrication, how it can support your technology development. I invite your contact, and I'm happy to speak to you about your particular project needs. Visit FactService's website for more information about specific processes and capabilities within the FACT network and news about events and other webinars that are planned. So there's maybe 1 minute left for any remaining questions from the audience. And let's give maybe a few seconds for people to send them in if you have any. Okay, any questions coming in? So I will call the conclusion of the webinar and thank everyone for your attendance today. Until next time.